So now to this second one, 3.3 number 2. This is about composite linear maps. In this case, I'm talking about the combination of two different matrices to represent the overall effect of a two-step linear mapping, actually. So let's look here. We have one linear map, which is called T1, applied to a vector X, and it's given as this matrix A1 applied to vector X. So, and the same thing for the second step, you could say. So now we have, accordingly, we have a matrix A1 and A2, and now we consider another linear map, which is just called T, and it should be the concatenation of these two mappings. And as you see, you know this symbol. This is meant for, do you say concatenation? I think so. Like the nesting, okay? What it means is that we apply this transformation, let's call it just transformation first, and then afterwards the other, okay? So in the order, first do this and then do this. And now the exercise is to find a matrix which defines this transformation, this mapping, but by using just a single simple quadratic matrix, by the way, okay? So we are looking for a matrix which is appropriate for representing this whole combined linear mapping. So if we multiply this matrix to our source, to our pre-image vector X, we will get the correct image vector. That's what we want, okay? That's all we want. What is this? What is this? No, strange. Ah, this is from the, probably from the screenshot, whatever. Okay, then now I start and I tell you, if you're not so familiar with this notation, perhaps it's better to put it in a more explicit form. So I call my image vector Y, okay? Just for fun, it's called Y. And then this is equal to our a certain matrix, or let's say to this transformation T applied to the pre-image vector X. And now, exactly speaking, it means that transformation 2 has to be applied after applying transformation 1. So this is T2 of T1 of X. That's you know this notation probably from functions, okay? From nested functions. That's what I meant, nesting of two operations, okay? And then, so in the end, it's just like applying matrix 2, this one, after applying matrix 1 to the pre-image vector X. So that's all. And now I use the associative law, which is always valid even for matrix operations, for matrix multiplication. That's nice to know. Please be careful, because you know that, that the commutative law is not anymore valid using vector algebra, matrix algebra. With matrix multiplication, you have not at all a commutative law, but you have still associative and distributive laws. So what can I do? I can set my parentheses differently and combine these two matrices, and I just call the result matrix B to get a combination matrix which fulfills the whole requirements, all the requirements of this exercise, okay? So this is what I do. I multiply these two matrices just by the same principle, which I called ERTEC, every row times every column, okay? So I start, as always, with first row, first column, and this is -1 times 1 plus 1 times 2. So -1 plus 2, which is 1. This is my element 1, 1, and so it goes on, okay? I stay with the first row, but I move to the second column. This is the usual way to go through rows, and then row by row, okay? In the resulting matrix. So first row times the second column, -1 times -2 is 2, plus 1 times 2, 2 plus 2 equals 4, this is this one, okay? Then second row, first column, 0 times 1 plus 2 times 2, 0 plus 4 equals 4 again, and second times second, 0 times minus 2 plus 2 times 2, 2 times 2 is 4, and that's it. That's the combination matrix B, which will allow us to transform the pre-image vector X to immediately to its image vector Y. Okay, so that's what we do. We now use this matrix B, applying it to our pre-image vector. Now, first row, first column, 1 plus 4 equals 5 here, and 4 plus 4, you see, 4 times 1 plus 4 times 1 equals 8, and that's it. The image vector is 5, 8. Without any proof now, the only thing I used is the associative law for matrix multiplication. So that's it. That was the first one. And the same is here again to be done with a little larger matrices and vectors. But since you understood the principle, I hope that you will agree it's okay if we just leave away the second part for now. I leave it for you. If you haven't made it by yourself, you didn't make it alone, okay? Now you have the chance to exercise this one to try again, okay? By your own. Here's the solution if you want to read after. And so I jump over this, and then we would, let me look at the clock, okay? We would just do one more step and proceed to this one. By the way, this is just a hint. Please look by yourselves. There are some people who use this scheme. It's quite nice if you're not so easy with using my ERTEC principle. It's nice to do this. If this is matrix A and this is matrix B, you can reorder them in a way so that the rows of A look like, it's like if I go along one row of A and then one column of B, these are, let's say this is a row of A and a column of B, which I want to combine. Then you see that the crossing point where these lines cross, this one is the position where the resulting number comes, is to be placed. So this holds for all combinations of rows and columns, rows of A and columns of B. So it's a nice scheme to use. But moreover, because you learned about transposed matrices already, it's also very nice to find the geometric reason, if you want, why is it that the product A times B is the same as the product B transpose times A transpose, which is one of the valid rules for transposed matrices, as you learned. And perhaps you wonder, why is it? Oh, by the way, I have to write C transposed here. Oh, and so it means it's not the same. What I wanted to say is, if you transpose them both, you have to change the order, and then you get the resulting matrix transposed. But here you see why it is. Because if you do the following, you just need to flip this whole picture around. You know what I mean by flipping? It's like I have to make an axis rotation around, three-dimensional, you could say, or just a mirror. I take a mirror along this axis, and then you see what results is this, and you also can see that the numbers are mirrored now. I hope you can read mirror numbers. I think so. But you see that these numbers exchanged positions in an appropriate way, so that after all I must take rows of B transposed and columns of A transposed. You know what transposing means? It means to mirror the matrix elements on the main diagonal. And so also the C matrix has been mirrored to C transpose. So I think it's quite nice to understand this connection here. This is taken from Wikipedia. I never want to use foreign sources without telling you. Okay, so that's fine.